Welcome to Tech Edge Market, where technology meets real-world engineering. Today we explore one of the most important machines in modern industry, the three-phase induction motor. From factories to automation systems, this machine powers everything around us. But how does it actually work? How does electrical energy transform into mechanical motion? Let's take a closer look. This is a three-phase induction motor simulation, designed to demonstrate real-time operation, internal structure, and performance analysis. In this model, we can interact with the system and observe how different electrical and mechanical parameters affect motor behavior. On the left side, we have the motor parameter controls. Here, we can adjust the supply frequency, which directly affects the synchronous speed of the motor. We can also change the load torque, representing the mechanical load applied to the shaft. Additionally, the animation speed can be modified to better visualize the internal working process. On the right side, we see live performance metrics. These include synchronous speed, rotor speed, slip percentage, output power, and overall efficiency. Synchronous speed is determined by the supply frequency and number of poles. However, the rotor always rotates slightly slower. This difference is called slip, and without slip, torque cannot be generated. Now, let us understand the working principle. When a three-phase AC supply is applied to the stator windings, a rotating magnetic field is created. This magnetic field rotates continuously inside the motor. As it rotates, it cuts the rotor conductors. This induces current inside the rotor, and this induced current produces its own magnetic field. The interaction between these magnetic fields produces torque, and the rotor begins to rotate. In cutaway view, we can clearly see the internal construction. The outer part is the stator. It contains laminated cores and three-phase windings. These windings generate the rotating magnetic field. Inside the stator, we have the rotor, a squirrel cage structure made of conductive bars. No direct electrical connection, yet current is induced automatically. Now focusing on the stator windings, they are arranged precisely to produce a balanced three-phase magnetic field. This field continuously rotates, driving the motor forward. Next, the rotor cage. As the magnetic field cuts across the rotor bars, current flows through them. This interaction produces torque, and the rotor spins. The shaft delivers mechanical power. Bearings ensure smooth rotation. Cooling systems maintain safe temperature. Now let us observe the waveforms. Three-phase signals separated by 120 degrees. This phase difference creates the rotating magnetic field. The phasor diagram shows vector relationships rotating together, forming a circular field. Next, the torque speed curve shows how torque varies with speed. The starting torque is high. It reaches a maximum known as breakdown torque, then gradually decreases near synchronous speed. Now the power flow, electrical input, is converted into mechanical output. Some energy is lost as heat and friction. The remaining energy becomes useful power. Thermal monitoring ensures safe operation, preventing overheating and system damage. Overall, the three-phase induction motor is simple, reliable, and efficient, used across industries worldwide. This is how electrical energy becomes motion through induction, rotation, and torque. This is the working principle of a three-phase induction motor.
This is the power of industrial automation. Simple, efficient, and built for reliability. If you found this helpful, make sure to like the video and subscribe to Tech Edge Market for more real-world engineering content. And don't forget, stay curious, keep learning, and stay on the edge of technology.